Okay, so we just learned how to describe systems of a general spin, well, spin higher than 1/2. And the motivation for that is going to be that, so far we've been dealing with these two spin 1/2 particles, and we've just been labeling the states by the z components of the spin of the individual particles. And, this basis is based on those measurements. So if you can measure these z components of both particles and then get either both up, one down, one up, one down, or both down. And so that naturally leads to these 4 basecads. But rather than measuring the individual z components of the angular momenta, what you could do is measure the total angular momentum and total z component of the angular momentum of the entire system. And for each set of observations you make, there are a different set of basis vectors. So we saw last time, or for our just systems of one spin 1/2 particle, we could either use the spin z basis or the spin x basis or spin y basis. And those all corresponded to different, things you could measure. You could either measure the z component or the x component or the y component. And there were different bases for each of those different measurements. So this is just the same kind of thing. This basis corresponds to the individual components of the spin being measured. And there will be another basis that corresponds to the total spin and total z component of the spin. So how can we find that other basis? Well, it makes sense that if both of our, in this state of both of our particles being spin up, well, you would think that their angular momenta would kind of add together. So it's not crazy to assume that this state, where we have the individual particles both being up in spin, both being spin up, that would act like a system with total angular momentum 1 and 1, or well, h bar. When I say 1, I mean h bar, and 1 along the z direction. So in other words, this basis vector is really the same as this other basis vector. And then similarly, we would expect that the down, if both of our particles are down, then that would correspond to a system or a state with total angular momentum 1, but -1 in the z direction. So how can we really verify that this is true? Well, we saw last time, we were working with the spin raising and lowering operators, and we saw that for spin 1 systems, we had 3 states. We had 1, 1, 1, 0, and 1, -1. And we could get from one to the other by either applying the lowering operator to this state or applying the raising operator to this state. So there should be, if this is a system with total angular momentum 1, we should have another state kit with, 1, 0. And what we can do is define a raising operator, which will just be the sum of the individual raising operators, and then act that on our 1, -1 state. And if we do that, we saw last time that what we should get is square root of 2 times h bar times the 1, 0 state. So we can work this out because s plus is just this, and then my 1, -1 state is just my down, down state. And if I work this out, then so s1 plus will just flip this down to up, and then s2 plus will flip the second arrow up, and I'll get an h bar because these are the spin 1/2 raising operators. And if I factor out this h bar and then multiply and divide by square root of 2, I can read off here that my 1, 0 state should just be 1 over square root of 2 times my up, down plus down, up state kits. And it's not a coincidence that this is one of the eigenstates we found for the Hamiltonian we were working with before. But so this is, so it's what we're saying is that this system that is a linear combination of the first particle being spin up and the second particle being spin down, and the first particle being spin down and the second particle being spin up, it is the same as a state with total angular momentum 1 and 0 along the z direction. And then there is one more state, which will be well, first what we want to do is to confirm what we've been doing is act our S plus on this 1, 0 state. Because we know that if we act S plus on it, we should get square root of 2 times h bar times this state. And if you work it out, you will find exactly that. So we have a basis, a different basis for our system of 2 spin 1f particles that is acting like a spin, or at least part of the basis is acting like a spin 1 system. We get the 3 states that we would expect out of a spin 1 system. But, we have 4 basis vectors in total, so we have the 3 from the spin 1 system. The last one we'll have is the 1 state that we would have from the spin 0 system, which will be the other eigenstate we found from the problem we worked before. So just a minus sign instead of a plus. And the way you could verify that this has 0 angular momentum is just by applying the raising and lowering operators to it, and you would find that you get 0, which is a sign that it has 0 angular momentum. So what this is saying, all it's saying mathematically is we have 2 different sets of basis vectors, one corresponding to the measurements of the individual z components of the spin over particles, and one corresponding to the measurement of the total angular momentum and total z component of the angular momentum of our system. And it's traditional to label them like this. So this is the these vectors are the S1z, S2z state cats, and these are the SM state cats. So this is first particle z component of angular momentum, second particle z component of angular momentum, and then for these ones it's the total angular momentum and the total z component of the angular momentum. And the advantage to doing this is, well, we already saw that these are the eigenvectors for our problem before, and that will allow us to more easily solve that problem.